Good day everyone, this is your Materials Engineers reporting live for the course EDI4663, Introduction to a Material Analysis. Today's main story focuses on a technique that quietly saves industries from big problem, differential scanning calorimetry, and usually known as DSC. DSC is a thermal analysis technique used to measure how much heat a material absorbs or releases when it is subjected to controlled temperature changes. In other words, when materials are heated and start to behave differently, the DSC is there to record the evidence. This technique is widely used in industrial and pharmaceutical field because it provides critical information such as melting behavior, crystallinity, purity, and thermal stability. These properties may sound technically, but in real life, they determine whether a product works properly or causes serious issues later on. We don't know. In real-world industry, materials failure or degradation is not just inconvenient. It can lead to quality problem, safety risk, and very unhappy customer. We don't want that. That is why reliable techniques like DSC are essential for quality control and decision making.
I represent a plastic manufacturing company that produce polyethylene-based products such as container and plastic material. Recently, our company received a batch of raw polyethylene, but we are unsure whether it pure high density or low density. This is such a concern because different types of polyethylene have different melting behavior, strength, and processing characteristics. Using the raw material may affect product quality and performance. Therefore, we require a reliable analytic technique to identify and verify the quality of polyethylene material.
In our case, we are concerned about the stability of aspirin tablets during storage. Aspirin is sensitive to heat and moisture, and improper storage may cause degradation. Degraded aspirin can lose its effectiveness and may pose risk to patient. Therefore, it is important for us to determine whether the aspirin samples remain pure and stable before they are released to the markets.
We use DSC. In this SC, a small amount of sample is placed in a sample pan while an empty reference pan sits beside it. Both are heated in exactly the same way and the DSC measures indifferent in heat flow between them. When the material starts doing something interesting such as melting or crystallizing, it will either absorb or release heat. These changes appears as peak on a DSC thermogram. Endothermic peaks mean the material is absorbing the heat, while exothermic peaks mean it is releasing the heat. By reading this peak, we can understand how the material behaves when the temperature goes up before it causes any real problem.
From a laboratory perspective, DSC requires only a small amount of a sample, usually a few milligrams, which is made with a fast, efficient technique. The sample is sealed in the aluminum pad and placed in the DSC instrument. A controller heating rate applied to ensure accurate and reproducible result. The DSC curve obtained a provide value information such as melting temperature, crystalline purity, and thermal stability. The first application involves the thermal analysis of polyethylene. Polyethylene exists in different forms such as LDPE and HDPE. LDPE has a more branched polymer chain, while HDPE has a straight and more closely packed chain. When analysis using DSC, LDPE typically show a broader melting peak at lower temperature, whereas HDPE show a sharper melting peak at higher temperature. By comparing the DSC curve and sample with knowing reference curve, we can identify the type of polyethylene.
Based on the DSC result, we observe sharp endothermic melting peak at a higher temperature. This indicates a high degree of crystallinity, which is characteristic of HDPE. The sharp peak also suggests that the material is relatively pure and uniform. This information is important for manufacturers because the melting behavior or crystallinity of polyethylene directly influence processing, conditioner, and final product quality.
Based on the DSC analysis and the explanation given, we can confirm that the military sample show the typical demand behavior of high quality HDPE. The graph clearly show a sharp melting rate at a higher temperature, which tells us that the material is highly crystalline and persistent. In simple terms, this means the plastic is behaving exactly how good HDPE should behave.
The second application involves the barometric analysis of aspirin using DSC, where aspirin typically exhibit a sharp atomic peak at around 135 degrees Celsius, which is corresponding to melting point. This sharp peak indicates high purity. However, if aspirin is exposed to heat or moisture, this may decrease into a salicylic acid and acetic acid. This degradation can be detected by a change in the DAC curve, such as peak broadening, and shifting.
In this case, the DSC curve of aspirin sample shows a broadened peak and slight shift in melting temperature, indicating degradation. From a quality control perspective, this suggests that aspirin may no longer meet the effectiveness and safety standard. Therefore, based on the DSC analysis, we conclude that this batch of aspirin should be rejected to ensure patient safety and product quality.
In conclusion, differential scanning calorimetry is a powerful and reliable material analysis technique. Through polyethylene analysis, DSC allows manufacturers to identify materials type and ensure quality control. Through aspirin analysis, DSC enables pharmaceutical companies to assess purity, stability, and degradation behavior. This application demonstrates the importance of DSC in ensuring product quality, safety, and performance across different industries. Thank you for your attention.